Mathematica to look at an application of systems of linear equations, and that's with polynomial curve fitting. There are other approaches to polynomial curve fitting, but we're just going to use this as an application for systems of linear equations and show how Mathematica can be very useful in determining polynomials that pass through certain points. So, for example, we want to know the quadratic polynomial, and we don't know the coefficients, but we do know that the graph passes through these 3 points, 1, 4, 2, 0, and 3, 12. Alright, so just to get a visual, I'm going to use a list plot here just to plot those 3 points, and so you can see them on the screen. And I'm going to label this list plot as A because I want to reference it later on. Alright, so there's my plot. And so to figure out what quadratic function passes through these 3 points, I can set up a system of linear equations just like this. I know that if x is 1, my output's 4. So if I say p of 1, I know that's going to be a sub 0 plus 1 times a sub 1 plus 1 squared times a sub 2, and that's going to equal 4. When I plug in 2 in for x, I end up with 0. I have a0 plus 2a1 plus 4a2 equals 0. And similarly, when x is 3, we end up with a sub 0 plus 3a1 plus 9a2 equals 12. Now we can take that system of equations, just put it into a matrix, and reduce. So there we have our output. And just quickly, if you haven't done this before, row reduce is a very useful function when dealing with systems of linear equations. And I put in my matrix as a list of lists, where each row is an element of a list, which is a list itself. And then I use / matrix form to get a nice matrix output. And the way we read this then is that a sub 0 equals 24, a sub 1 equals negative 28, a sub 3 equals 8. So our polynomial then is 24 minus 28x plus 8x squared. And I would like to plot that with my list plot just to get a good visual of that curve that passes through the 3 points. Now to display 2 different kinds of plots together, I need to use the show function, and I always recommend using the outside-inside writing style. So I'm going to open up the brackets and close them immediately for the show function. That way at the end I don't get confused on where all those brackets and parentheses are going. And I'm going to plot with the plot function this polynomial we just came up with. And I want to make sure that I include the range of x values. So we were going from 1 to 3, so 0 to 4 should be sufficient. And I'm also going to add a little bit of aesthetics through plot style and directive. I'm going to say red, I want it thick and dashed. That'll give me a nice thick dotted line that's red, and then comma A. And that A, remember, is that list plot that we originally had. So now I hit Shift Enter, and there we have it. We have the 3 points, and then we have our dotted red quadratic that's passing through those 3 points. Pretty cool. Now that's our example. Now we want to go through some exercises that cover a similar topic. So now for exercise 1, we're going to find a cubic function, and they gave us 4 points this time. So let's build our matrix here. I'm going to call it matrix C. So remember, when this time I'm dealing with a cubic function, and when I plug in 0 for x, I get 1. So I know I have a sub 0 times 1, 0 times a sub 1, 0 times a sub 2, 0 times a sub 3, and that's going to be equal to the value 1. When I plug in negative 1, I have the constant 1 for a sub 0. And if that's confusing, just remember it's the same idea that we had here with the system of linear equations. When I plug in 1 here, I had a sub 0, a sub 1 times x, a sub 2 x squared. Now we have x cubed, so we have an a3 x cubed as well. And so this is the 1 is my a sub 0. I have negative 1 times a sub 1, negative 1 squared times a sub 2, negative 1 cubed times a sub 3 equals 1. And similarly, we have 1, negative 2, negative 2 squared, negative 2 cubed equals 3, and 1, 2, 2 squared, 2 cubed equals 10. There's my matrix C. Alright, now we just need to row reduce this guy in matrix form, and there we get our answers. Okay, so my cubic polynomial is 1/8 x cubed, and so on. I'm going to show a plot of that cubic and a list plot of the points that we want to pass through. Similarly to our example, I'm going to first define my cubic here. So I had 1 plus 5/4 x plus 11/8 x squared, and so on. This time I want to include all my points. I'm just going to go from negative 10 to 4, And I liked the aesthetics from last time, so I'm going to use the directive again. Red, thick, and dashed. Okay, now on my list plot, I could have defined the list plot separately and called it a variable. I didn't, and that's okay. I just need to be careful to list out my points. I had 0, 1, negative 1, 1, negative 2, 3, and 2, 10. And there we have it. There we have my cubic function passing through the 4 points that we clarified. I hope that makes sense, and I hope that you see how cool this is that we can do this. You just give me 4 pieces of information, x and y, and now I can find a polynomial that fits through those points. We use this a lot to estimate data. We call this interpolate data between our given data points. So for example, at 1, I have a decent estimate of what was happening at 1, depending on my polynomial. Alright, so now for exercise 2, this time we do the same thing, but they only give me 3 points. Alright, so I'm going to define a new matrix. I'm going to call this matrix D. And it's actually very similar to C, so let me just copy C. And the difference is, this time I do go through 0, 1. I go through negative 1, 1, and negative 2, 3, but we didn't specify the point 2, 10, so I'm going to delete that row out of my matrix, and now just do the same thing we just did. So I'm going to row reduce D, and this time matrix form. Okay, and when I row reduce, this time I don't have a unique solution to this system, which kind of makes sense because I have 4 unknowns but only 3 equations. So what this means then is I get to pick what my x4 value is going to be. So we make it something generic like a. And let's go ahead and make a polynomial. So I'm going to call this dp. We're going to define our polynomial to illustrate what I'm talking about here. I know my constant term is 1 because I have a sub 0 equals 1. Now the others I don't know exactly. So I get a choice to pick for my leading coefficient. Because see, this pivot 1 represents a sub 0, that's a sub 1, and that's a sub 2. We don't have anything that represents a sub 3. We're allowed to pick what a sub 3 is going to be. I'm going to let a sub 3 be 1, so I get x cubed plus, and then the others are determined from that. So you have to imagine, this is negative 3 times a sub 3. We said a sub 3 is 1, so that's negative 3, and then if I equals 1, so if I move this over, I end up with 4 for a sub 2. And similarly, if I imagine that this is negative 2 times 1. So I have x sub 2 plus negative 2 equals 1. I get that x sub 2 equals 3. And then, like we said earlier, I do know that a sub 0 is 1. So there's my polynomial. Now, you could pick a different polynomial if I just change my value of a. We let a be 1. This is what we end up with. Does this work? Well, let's check it out. So I'm going to show function again. I want to plot dp of x. And I just want to make sure I go through the appropriate x values. And let's stick with our plot style again. And then let's get our list plot. And this time we're going through 0, 1, negative 1, 1, and negative 2, 3. And I realized I made a mistake here. This is plot label. I meant to say plot style. Sometimes I get a little happy with the tab key. Aha, and there we have our nice graph, red dotted line passing through the 3 points that we wanted. Now again, I could have changed the value of a and gotten a different cubic polynomial going through the same points. So for example, let's let a sub 3 be 2. So now I have 2x cubed. And if I'm imagining this, that's going to be a negative 6 added over. We end up with 7x squared. And then negative 2 times, we get a negative 4. Adding over, we get 5. This polynomial is also cubic and will also pass through those same points there. I just adjusted my graph, still passing through the same 3 points. So how do I know when I get a unique solution and when I don't? In the example 1, we got 4 points. It determined a unique cubic that passes through. Exercise 2, we only had 3 points, and so we had a lot of cubics that could pass through those 3 points. Here's the key. When you have n points, then an n minus 1 degree polynomial will be unique that passes through those points. Okay, but for higher degree polynomials, There are a lot of them that pass through those endpoints. So for example, this time let's consider 1, -4, 3, -5, and -2, 0. We want to find some polynomials of degree 2, 3, and 4 that pass through these points, and we're going to plot them all together. Okay, so since there are 3 points, I know that I only have one degree 2 polynomial that passes through those. But for 3 and 4, we're going to have options. All right, so let's start making our matrices. So I'm going to call this C2, and this is my quadratic. If I have a unknown quadratic, when I plug in 1 for x, I get -4, so that's going to be 1, 1 squared, 1 cubed, that adds up to be -4. When I plug in 3, I have 3, 3 squared, that adds up to be -5. And for -2, 1, -2, 4, and that adds up to be 0. Let's go ahead and row reduce. Alright, and we get unique solutions because we know there's a unique quadratic that passes through those. I'm going to call this guy D2. Let's go ahead and define it. -7/6x plus 1/6x squared. Alright, there's our first one. Now let's do the same thing with the others. So we have C3, and the only difference now is I have 1 in the first, 1 squared, 1 cubed equals -4, because C3 is a cubic polynomial that we're seeking out. 1, 3, 9, 3 cubed equals -5. 1, -2, -2 squared, -2 cubed equals 0. And we do the same thing. I will reduce that. And now we get non-unique solutions. So now we have options, but I'm going to make it easy on myself and let the a cubed be 1. So now I have x cubed plus, and now imagine this equation says a sub 2 plus 2a sub 3 equals 1/6. So that means a sub 2, since a sub 3 is 1, we have 1/6 minus 2. I'm not going to even do the arithmetic. I'll let Mathematica handle that for me. X squared. And I'm at x cubed for my first term here. And then we play a similar game. Alright, now we needed a similar thing with a 4th degree polynomial. So now we have 1 in the first, 1 squared, 1 cubed, 1 in the 4th equals -4. And it's good to read this out to yourself because it is getting confusing here. 1, 3, 3 squared, 3 cubed, 3 to the 4th, and that has to add up to be -5. And then 1, -2, -2 squared, -2 cubed, -2 to the 4th adds up to be 0. And I know that when I row reduce, I'm going to have 2 options now. I'm not going to have enough pivot columns to get all 5. I'm only going to be able to determine 3 of them. I have an a for a sub 4 and a b value for a sub 2 if I'm doing parametric solutions. I'm going to let both of those be 1. So then what that tells me is I have 1 x to the 4th and 1 x cubed, and then after that I get options here. So I'm saying this says a sub 3 plus 2 times a sub 4, which we said is 1, so that's 2, plus 9 times a sub 4, which we said was 1 as well, so that's 2 plus 9, which is 11. Subtract that over, we have 1/6 minus 11 x squared plus -7/6 minus 9 x, and then -3 plus, what is that, 18? Okay, now we got to plot all this together. So I'm going to show again. I'm going to have a plot and a list plot. I'm going to go ahead and list those out. And in my plot this time, I want to plot 3 different polynomials. So I make a list, and I'm plotting d2 of x, d3 of x, d4 of x. And I'm not going to mess with the coloring here because I do want them to be different colors so I can tell which one's which. We're going from -4 to 5. I think should be good enough. And I will make them bold at least though. So let's do directive thick. Alright, now on my list plot, I just need to put in the points that we're passing through. 3, -5, and -2, 0. And I notice here that the D3 is listed as blue, and I'm looking at it again. I accidentally defined D2 twice, so let me go back. This should be D2 of x, D3 of x, not D2 of x. And now I think I should be okay in my plot. Yeah, so I get all 3 curves. The blue is D2, that's the quadratic. The yellow is D3, that's my cubic. And green is my fourth degree polynomial, all passing through those 3 points. Now, a numerical analyst would want you to use the lowest degree polynomial possible, so they'd want us to use the quadratic. But I think it's worth mentioning that there are other polynomials that pass through those 3 points. So we do know that there's some sort of built-in error when we're doing interpolation. Now, in the previous example, we had options for our third and fourth degree polynomials that we wanted to pass through these 3 points. And both times we picked our leading coefficient to be 1 and then determined our coefficients based upon that choice using our reduced matrices. But now in this question, what we want to do is we want to find all of the degree 3 polynomials that pass through those 3 points. And we're actually going to use a manipulate function to visualize this family of polynomials. Okay, so this time what I want to do is I'm going to make a list of points, and I'm going to call it A points. You don't have to label it that, that's just what I'm picking. And then I need a matrix just like from the others, so I'm going to call this A matrix. And again, we're setting up a cubic polynomial, so we want 1, negative 2 squared, negative 2 cubed, that has to equal 1, and then 1, 0, 0 squared, 0 cubed, 3, and then lastly 1, 2, 2 squared, 2 cubed, and that adds up to negative 1. Okay, so then when we row reduce our A matrix, we end up with this expression. And if you notice here, we again have a choice for our A4. We do know that A sub 3 and A sub 1 are fixed. Alright, now here's what we want to do. We want to again show, we want to have a plot and our list plot. Now in my plot, what I want to do is we're trying to plot all degree 3 polynomials that pass through these points. So in the past, we've just let 1 stand in for our leading coefficient. This time I'm letting the leading coefficient be A. So this polynomial would be ax cubed minus, now let me think, if A sub 3 is A, then, well, here it doesn't matter. A sub 2 is going to be negative 3/4, so I have minus 3/4 x squared. But then my linear term does matter. I have negative 1/2 minus 4 times whatever my leading coefficient is, which is A. And then my constant term is going to stay at the value 3. We're going to let this go from negative 4 to 5. And let's do a plot style with a directive red, thick, and dashed. I also, since I'm going to manipulate these plots, I would like the aspect ratio to stay consistent. So I'm just going to say aspect ratio 1. And to help with that also, we're going to add in a plot range. Now what the plot range does is it specifies that I want x to run from negative 4 to 5. And let's let our y stay fixed from negative 10 to 10. So this will help just keep our plots looking the same as we change our value of a. And I believe I'm missing a bracket after my plot function. And now I'm going to wrap all of this in the manipulate function. And I'm going to vary, what am I varying here? I want to vary what the value of a is, my leading coefficient. And we can go from negative 3 to 3. And so this will calculate, I'm calculating these polynomials. Every single one of them will pass through my list of points here. And as I change the value of a, which I do with the manipulate function, we're going to be able to see how these cubic polynomials change but still pass through those 3 points. So let's take a look. Okay, so look, there is a cubic function that passes through the 3 blue points. And as I drag a along, this is negative 3. As I drag a along, look at that. We still have cubic functions that are passing through those points, which is pretty cool. All right, now one thing I need to point out though is, look, when a is 0, so if I let a be 0, what happens? So if you look at this, if you look at our polynomial, if a is 0, the x cubed goes away, and we end up with a quadratic equation. And notice that my graph is parabolic. What would be a nice idea is to plot all of this, but also have our parabolic function. And that's exactly what exercise 5 wants us to do. So plot the unique parabola that passes through those 3 points. Okay, so let's call this a quad for our quadratic. And we're going to set it up the same way we've done the others to figure out what our unique polynomial is. And here we have it. So then we know that our unique quadratic that passes through these 3 points is going to be negative 3/4 x squared minus 1/2 plus 3. I'm going to just copy my previous input, and I'm going to add in here this new information. So the way I could do that is I'm going to make a list of the polynomials that I'm plotting. I have the one that changes with a, the cubic, and then I'm going to have my quadratic. Most of this stays the same, except that I want my plot style to also change. So the way I can do that is I can make a list, and the first entry applies to the first thing I'm plotting, which is the cubic. The second one, I'm going to say directive blue thick. This will apply to the second function I'm graphing, which is the quadratic. So I'm going to shift enter. There's the blue quadratic that we get that passes through those 3 points. And notice that as a gets closer to 0, they line up. And in fact, we really didn't have to row reduce a matrix to get this quadratic, because notice if I had taken this cubic and I let a be 0, what happens? I end up with negative 3/4 x squared minus 1/2 x plus 3, which is exactly what we got when we did the row reduce method from earlier. But now we can see all these cubics, and we can see the unique quadratic that passes through them. Now again, this is just an exercise to show how systems of linear equations can be useful. I hope you can see how they can be useful, and hopefully you can see that this is an interesting idea. If you have any questions, I'd be glad to help. Just let me know, either reach out to me or leave a comment below. And thanks for watching.